So yeah, just a little intro. So Paul and I kind of go back. We've never talked a whole lot, but over the years, every few years we'd have a phone call conversation. And I think Paul, you started like pipingdesign.com back in around 2000, early 2000s, like '02 or so.
Yeah, uh, 1998, I think.
98.
And
So that's interesting because
yeah,
that's exactly when our we started our company, we being my wife and I, and that's who we still are, running our huge company, just two people. So we started in 98 with a website, it was like Alta Vista and some of these search engines you never heard of anymore, dmoz.org and all. Google wasn't even around back then. But like Paul, we got a pretty early start in 98, and so we got a pretty decent, I guess, listing on the web. So maybe you can find us better than a company that just started like a few years ago. Maybe not. Really depends on the keywords that somebody keys in. But yeah, so I used to teach at. I'll just bring up my background a little bit here. So I'm going to click on about LMNO engineering. Let me go ahead and I'm going to key in just so I don't. Well, I'll get to the software later on. Because I am going to give everybody a free PIN number to access the software as we go through it. So I'm going to talk about, some engineering software we have that might help you with your problem with solving your piping problems, so on. But my undergrad was in nuclear engineering from Purdue University in Indiana, USA, back in 1986. So you can kind of start dating me. I'm 60 years old. And I worked at a nuclear power plant, actually two of them that were side by side, Salem and Hope Creek nuclear power plants back in the early 1980s. After I got my bachelor's, I decided to switch fields a little more to environmental and water resources engineering. And my wife took me down to Dallas. She's also a nuclear engineer, and so she got a job for Texas Utilities down in Dallas, Texas. So I followed her down there and worked on a master's degree in civil engineering with a focus on environmental and water resources, did a lot of outdoor projects, flow measurement, things like that. And I worked for an air pollution consulting firm called Trinity Consultants, which only at the time had two offices, Dallas and Kansas City in the USA. Now they've got about 20 offices. So we did air pollutant modeling, dispersion modeling using EPA software that predicted concentrations of pollutants at the fence lines or wherever offsite for companies that were trying to get permits to have new processes or modify existing processes for industrial facilities. We did a lot of work for companies in Texas and Louisiana. And from there, I decided I wanted to continue my education. So I went to Iowa State University, also in the US, and got a PhD in environmental engineering in '93 and did research in groundwater contamination and groundwater flow, but actually not actually groundwater, but air above the water table. So generally, we still sort of call that the groundwater field, but it was really had to do with removing pollutants or getting an understanding of airflow through soil that's above the water table. Because a lot of a lot of contaminants from gasoline stations or from industrial facilities are volatile. That is, they evaporate readily, and so they migrate from the groundwater to the vadose zone, which is the soil above the water table, also called the unsaturated zone. And so we installed some wells that were above the water table to suck out, put some blowers on top and sucked out the contaminants. I actually didn't work at contaminated sites. We were just trying to get an idea of the fundamental equations and flow of air through. It was very clayey soil, glacial till soil in Iowa. So anyhow, from there I sent out resumes and landed a job at Ohio University here in Athens, Ohio. Still I'm in Athens. I taught at OU for about 7 years, but started my left OU in 2000. Started our company in 1998 at OU. I taught lots of classes in um, fluid dynamics, wastewater treatment, water treatment, groundwater remediation, basic courses for civils and mechanical engineers like statics, strengths of materials, um, hydrology, rainfall runoff. So I kind of consider myself I consider our company a fluid dynamics company, but we do projects for civil engineers, mechanical engineers, chemical engineers, physicists, people, fire stations, farmers. So we're kind of do, municipal civil, which is wastewater treatment, like design of piping for gravity flow, and also municipal water distribution systems. So use pressurized conduit pipe network programs. We do some work in the hydropower industry. We do some work in the oil and gas industry, trying to predict pressure losses and design pipes and so on. And we get into water hammer, rainfall runoff, groundwater flow, a little bit of air pollution modeling, not too much. But we're just two people, so we can't just be a niche in like one specific area of like civil engineering or water distribution, something like that. So we're kind of general fluid dynamics. We do a lot of students who go through like their freshman and sophomore years at college for engineering, say, they're taking all this math, calculus, differential equations. They're like, I'm never going to use this again. But we do that stuff. So we solve triple integrals, we solve differential equations. We get companies that can't find somebody else to do a weird project that involves some mathematical analysis. And so, my wife Debbie, she's super good at math, and so she'll solve these weird differential equations and calculus problems. And one of the things I'll show you a little later on is our liquid volume in a tank that's at a sloped angle. And so the triple integral that she solved to solve that thing was super fun. So I think let me just go kind of through some of our consulting projects, and then I'm going to get into the software a little bit, make my screen a little larger here so you can see the fonts better. Feel free to interrupt at any time, ask any questions. I'm good with that. But just back in 2001, I guess that's as far back as I'm listening on consulting here. Pipe wall coatings, the impact of changing the roughness on the pipe wall. Let's see. So critical depth, normal depth, secant depth. This is open channel flow stuff. Probably not something piping designers get into too much, but I'll bet you do when you do get into tanks and discharge from tanks, and they're not always pressurized flow in out of tanks and so on. So you may have some open channel flow stuff. So these parameters and calculation become important. My first programming language was Fortran, and there's still ancient programs out there that are based on Fortran that people use. So we now know Fortran, Basic, Java, PHP. All of our calcs are now in PHP. Our calculations used to be, and Paul may enjoy this one. We originally wrote all our software as Java applets, and around 2008, right when we had the market crash or whatever, the credit crisis here in the U.S. That's about when websites quit support or browsers quit supporting Java applets. And so not only did we lose business from the credit crisis, but business went down because people couldn't access our software. So we spent about 3 years rewriting all 80 programs on our website in the program language PHP. And so now the sort of extra benefit of that is that all our software now runs on handheld devices, smartphones, and so on, whereas the Java actually just ran local on people's computers without them really knowing it. So it was very sort of machine specific a little bit. So anyhow, culvert sizing, pipeline pressure testing analysis, and kind of keep these a little bit general. And pipe network, water cannon. So, you're shooting water at, for whatever reason, I can't quite recall the purpose of their water cannon. Discharge coefficients, we get into this a lot. Like your standard discharge coefficient for an orifice is like 0.6, but they may be different depending on your Reynolds number, your viscosity, and so on. Piston engine analysis, some of this unsteady flow gets kind of interesting when you get into that sort of thing. High viscosity flows, siphon, we do quite a bit of siphon analysis, setting those up and how you get them started, how you get the flow started. Orifice coefficients at low Reynolds number, natural gas stuff, orifice and nozzles. Worked with a client on blood flow through the heart. Horses on a pipe sled to get it across a river. Partial flume, we do a lot with companies with flow measurement, like in open channels, streams, and so on. There's partial flumes. There's other types of flumes. There's weirs. So we do a lot of that design. We don't sell any of these devices. We don't sell anything other than our time and our software. We don't manufacture anything, but we do have a lot of relationships with companies that do make stuff, and they hire us now and then to come up with new rating tables for their latest flume or weir or something like that. or they just can't find, some stuff that's been developed back in the 1930s, 40s, and so you just can't find the original equation development for anymore. So what we have now are just equations with a bunch of coefficients that you have no idea where they came from. And so we get hired fairly often. Hey, we've got from a client who's got, hey, we've got this equation. We're not totally sure it's right, and we're not totally sure it's applicable to our situation. Can you like dive into it and figure out where this weird coefficient 0.03592 or whatever came from? And so we're good at that. We can recognize equations and kind of figure out if they're orifices, or if they're open channel flow or closed conduit, something like that. And we can back out the coefficient. It's usually a function of pi. It's a function of unit conversions. It's got some empirical coefficient in there too that we kind of figure out, track down. So, it always aggravates me, ASME, et cetera, reports where they just have the final equation and you just hope the constants in there are accurate. You're kind of taking it on faith because they don't have equation development in the back of any of those design manuals. It's really aggravating to me. We show all the equations on our website. We don't want it to be a black box. People can code up our equations in their spreadsheet. We try and, write equations and write software solving systems of equations that are not, sort of readily solvable by people. So that's how we kind of have our niche is saving people time by coming to our software. But we got the equations there for the most part, so people can key them up or solve them on their own. We just refuse to be a black box. Another thing is funny about our company. You guys might get a laugh out of this. Back when is ending your costs in 9. So this is just a little funny aside. So, why do we have gas for like, 249.9 a gallon or whatever? Well, it started back in like 1910 with the oil companies, I'm pretty sure. And ending something in like 0.9 sounds a lot cheaper than rounding it up to the next tenth. So 249.9 just sounds a lot cheaper than 250. We don't think so. We think we rationalize it and don't, but I'll bet we pretty much actually do succumb to that. And so we just so our software, we sell it as $40, $90, or $200. We might make more sales if we did like a $39.99, but we're our own company. We can do what we want. If we want to lose money by not having it $39.99, well, there you go. We're gonna round it to 40 just because I don't know. I consider it sort of intentional deception, but I probably got a lot of people on here who ended 9, so I hate to say that.
It makes your sales reports easier too, right?
I know they ended 0. I know, seriously. You tell a client $40, not 39. Come on, man. All the tax we build in, we pay. We have to pay Ohio sales tax for people from Ohio who buy software, and we just pay that, out of we don't charge anybody a different amount from each other, but we just do lose 3% or whatever on Ohio sales because we got to pay that ourselves. But that's fine. We don't want to have different costs for everybody. So yeah, hydraulics and hydrology, shear and normal forces. So, we get into some civil engineering calcs, forces, and using the momentum equation to determine forces on walls and so on. Water jets and oral surgery, that's kind of fun. Unsteady flow, always interesting, definitely more complicated than steady state. Detention basin sizing, we do a lot of that for civil engineers for developments. A lot of peak discharge calcs for rainfall runoff. HEC HMS and HEC RAS, they were developed by the U.S. Army Corps of Engineers to model flows in rivers and also rainfall runoff. We use those a lot. They're public domain, freely available to folks. Done some expert witness stuff. Fortunately, never been to trial, but I have been deposed a few times, so that's always fun. I do enjoy writing the reports for as an expert witness, but I really don't enjoy getting grilled by lawyers. We use this program, EPA Net, a lot. It's for water distribution systems, so pressurized conduits. It can also be used for gases. So we've used it for gases. It is a incompressible flow program. So if your gases undergo high pressure differences, it may not be appropriate, or you've got to pick a constant density to use, whether it's it's your low density or your high density if you're doing something that's compressible. Yeah, it works pretty well if you don't have too great of pressure differences. V-notch weir, so just another type of weir for open channel flow modeling. Valves, duct work. Let's see, culverts, a lot of choked flow. So piping design, maybe you get into this a little bit. Like if you've got gas systems, you get choked flow. If you have high velocities, um, so you end up with different equations than if you were not choked or compressible flow. Let's see. I kind of want to get into showing the calculations here. Oil skimming, heat transfer. We do some heat transfer. We had a client that had a really unusual twisted pipe situation to enhance heat transfer. So that was fun. We went to, there's a lot of heat transfer is basically an empirical field. So the heat transfer researchers do lots of experiments, come up with empirical coefficients for experimental being empirical being experimentally derived coefficients for heat transfer and equations that match the data. And so instead of being, I mean, it's sort of based on first principles, mass, momentum, energy conservation, but then based on lots of experiments because you just can't predict all of the real world behavior from the physical equations. So you got to go with experiments. And so you're basically trying to find a book or a paper that's got a situation similar to what your client has and pull off the equations from that reference source. Done a little bit of riprap. It's not that exciting, what size rock to put in a channel so you don't have that rock being washed downstream during a storm event, say. Inverted siphon. So this is like a wastewater or stormwater pipe that's running by gravity, but you got to get it from one side of a river to the other side. So you kind of go down and then back up. So this is one of our more popular programs. People just, don't seem to have this on their own from some other source. So inverted siphon, kind of one of our better programs as far as people using it. Forces on a drilling tool. So this was in the oil and gas industry. Manifold, this is pretty common where you've got pipes branching off other pipes. Pressure surge, so we get into this now and then. Water hammer. One of my favorite water hammer calcs, and I'll show it to you in a little bit, is just a super simple one. It just predicts worst case water hammer as if you're shutting off a valve like instantaneously. It gives you the worst case pressure. So maybe, and that helps you determine the pressure in your pipe and hence your pipe wall and maybe pipe material that you need. Reverse osmosis, that's getting a little more popular with fresh water becoming a little more scarce. It takes about 1,000 psi to get water through a reverse osmosis system, and so it's kind of expensive, and you've got to do that at pretty high flow rates because you've got to provide water for a city or whatever, and so a lot of energy, so energy costs. So that's the issue with reverse osmosis is the high energy costs right now. Drag force on divers. This was super fun. So a company wanted to know, if they've got a diver going down near a spillway, are they going to get sucked into the spillway and get trapped, or go through it like a big pipe? Usually there's a gate on the front, so you get trapped. But they wanted to know the drag force and hence the velocity on the diver, because if the diver can't hold on to whatever ladder, for instance, that's getting them down. Not a good situation. So kind of wanted to know what the velocity would be due to the water on the diver. ATC RAS, again, that's open channel flow modeling, Corps of Engineers program. So anyhow, this is fun. I'm going to show you this a little bit. I think this was mentioned in Paul's first email, was a partially full inclined cylinder on its side and what the volume is. So I'm open to, let me go ahead and key into the chat here, a PIN number, and it is 618-7316. So if you like, feel free to key that into our homepage, and Catherine put the homepage up there, LMNOENG.com. And so I'm going to go ahead and key it in so you can kind of watch me do it. So I'm going to key in 618-7316. And then it comes up with a page, the expiration date. So this one's expiring on Tuesday. So all of you, feel free to share it with your friends, whatever. It expires on Tuesday. But it'll enable all the calculations on our website through then. So now you can see I went back to the home page, and you can see, thank you for purchasing an online calculation subscription. And there you go. It's good until Tuesday. So what we have on our site and I don't really mean for this presentation to be an advertisement, but Paul was super nice about saying, "Hey, Ken, you want to talk about your website?" So I'm like, "Yeah, what the heck?" So we've got calculators. Like I was saying, we've been writing software since '98. I'm getting a little burned out, frankly, of writing new software, so I don't do it that much anymore. It takes a long time to write software, even a simple program. We put it through a lot of checks, and we and check it against known results of other people's work. Check it against, set up a spreadsheet to check it against a spreadsheet. Do hand calcs. We're big into hand calcs. We'll get clients, that'll send us a spreadsheet where they just keyed in like equations. And I'm like, come on, man. Where's your show? Just write down the equation. Give it to me by hand. Come on, write your equation by hand so I know, so I don't have to go chasing through all these cell formulas to figure out just what equation you ultimately used. Whenever we do a report for a client, they probably don't want all the gory details, but we show all the equation development that we use. And we always do at least one calculation with numbers, with units, by hand typed, call it by hand, that matches, well, if they want a spreadsheet, that matches the spreadsheet. And we'll do multiple equations by hand also. And, it just astounds me that a lot of people in the industry, other consulting firms don't do this. So somebody will send me something that they got from another consultant, and I'm like, where's the report that accompanies the spreadsheet? And it's like, well, it's a spreadsheet. I'm like, so I got to go chase through all these cell formulas to see what the ultimate equation was that was used. Kind of amazes me. But so that's what I would say for the state of the industry right now. Be really careful. I mean, write reports that support your spreadsheets and your software to show that it works. At least give me one hand calc that matches one type of your equation. For each type of equation, give me a hand calc with numbers. So I think this group is kind of more into pressurized conduits than open channel flow. So maybe I'll focus on that, but just generally, just the first overview here, we've got open channel programs, pressurized conduit programs. On the right, single pipes, compressible flow, specialty programs. On the left is more the open channel stuff. If you ever heard of gradually varied flow, which is like how water depth varies within a river if you have with a downstream or upstream boundary condition, as opposed to what we call uniform flow, where the water depth is constant. Uniform flow is an assumption most people use, like Manning equation, if you've heard of that, but it's really not a real life situation, but it'll get you close to real life water depths if you have a fairly uniform dimension channel. Open channel, hydraulic jumps, flumes, weirs for flow measurement, drag force, riprap. Then we get down, we've done hydrology, groundwater stuff. Let me start with the pressurized conduits. So one of our more popular programs, a lot of people have a program like this from some other vendor, or you've developed one on your own in a spreadsheet or something like that. But basically, we're predicting pressure loss or flow in a pipe. So these are just some scenarios here. For instance, maybe this is scenario A, you've got a pipe, and you've got to have a location 1 and 2 that you're going to. A lot of people will just go from like the outlet of a pump to a location and want to know what the pressure outlet from the pump is. Just be a little careful. Write the energy equation from between 2 points in the system. So the fundamental equation here, I call it the energy equation. On your left-hand side is like if you have a pump, the head of the pump, and then an elevation change from location 1 to location 2, draw a picture that shows your locations 1 and 2, and then write your energy equation from one point to the next point. So you've got the elevation change, the pressure change. S is not specific gravity here. It's weight density, like 62.4 pounds per foot cube for water, or 9810 Newton per meter cube for water. Velocity difference between the 2 points, velocity head, so they're squared. Friction losses, minor losses. So minor losses are due to like your pipe elbows and things like that, valves, and your friction loss is due to friction between the fluid and the pipe wall. And so just here's our default case. You can select all kinds of pipe materials, whatever. And water, we've got different fluids here. We've even got some gases, but just be careful with them because we're assuming a certain density for them, and gases can be compressible, and so that can change along the pipe length. So just here, just for fun, I've keyed in a diameter of 6 inches. So this would be an internal diameter for a length of 1,000 feet. Minor losses of 10. So this is a whole bunch of valves. Each valve is maybe 0.5. So maybe there's 20 valves in here or other stuff. Or I mean, not a valve, but maybe each elbow is around 0.5. Valves can be kind of all over the place depending how open they are. Elevation difference from one location to another, maybe a pressure difference. So maybe we're pumping from low pressure to high pressure, and maybe you already know your pump head. Usually pump head something you want to compute, but this is just kind of a default case here. So then it'll compute a flow rate and a velocity. In piping, not sure what SPED recommends, but I kind of use 3 feet per second to 10 feet per second as sort of a guideline for liquid and pipe, maybe 6 to 10 feet per second, something like that. Maybe a lot of people are on metric system here, so multiply that by basically 0.3, so about 2 meters per second or so, typical velocity in a pipe. And so, a lot of our customers want to know a pressure difference between 2 locations in a pipe. So you can kind of select, maybe solve for, if you know your flow rate, you can solve for a pressure difference. So maybe you put in your flow rate, just going to key in a round number here. So maybe you've got 800 gallons per minute, and this is a US gallons per minute. Be careful if you're in a country that uses like imperial gallons per minute, because there is a unit conversion there. More people are going to meter cube per second. Well, I guess maybe it's because we're working with folks in Canada. They're always giving us CMS, which is cubic meter per second. And then, so man, we are mixing units all. I don't know about other folks in the world, but we'll have customers with PSI and then meter cube per second, length in feet or meters. Everything's in different unit systems. I think ASME, I thought they were coming out with like getting rid of English units in their like latest. I don't know what the latest version is of the design manual, but is the US ever good? I was told in 4th grade, I remember this distinctly. This was back in like 1974 or something. My teacher said the US will be metric by 1980. I graduated from high school in 81. We weren't even close to being metric. And I go to college and at Purdue, and some problems are metric, some are English, so it's actually pretty good. We never in homework problems we rarely mixed SI with English systems, English units. On occasion, especially in design classes, you would get into that, but we do a lot of problems either English or metric. So I'm totally familiar with mixing a lot of units. The one unit that I think is underappreciated, and this is just kind of a fun thing, is the slug. I don't know if anybody out there has anybody heard of the slug?
I just heard that
Absolutely.
last week for some reason.
Absolutely.
Yeah, see, you guys are right with me on this. So a pound is a slug foot per second squared. In SI, a Newton is a kilogram meter per second squared. And people, if I give a client mass and slugs, they'll be like, what? What is this? If I'm doing for a client, if they want metric, easy peasy. I give them mass density kilogram per meter cube. And I can give them force in newtons, no problem. If I get somebody who wants English units, like here in the US, there's no way I'm going to tell them 1.94 slug per foot cubed is the density of water, because they're not going to know what I'm talking about. I'm going to give them 62.4 pound per foot cubed. They know that number. But that's a weight density. So if you have an equation that's got density in it, you've got to be really careful if that density in that equation is weight density or mass density. If it's mass density, you got to divide the 62.4 pound per foot cubed by 32.2 feet per second squared for gravity in order to get a mass density, which will give you can just punch it out right now. 62.4 over 32.2 gives you 1.94 slugs per foot cubed, the density of water, the mass density of water. But people in the US don't want slugs. Now, if you go through a university, you're using slugs.
Can I ask you, while we're looking at this equation, the pipe diameter, that's the inside pipe diameter.
Yeah,
a lot of our piping friends because pipe deals without constant outside diameter, the thickness determines the inside diameter. So
Yeah, I'm using a
you're
round. Yeah,
applying inside diameter here.
yeah, totally. I should have. Yeah, hopefully maybe I've got it in the definitions down there, but that says inside. But yeah, totally right. Inside diameter. And when I'm using a round number here, that's also kind of misleading because you rarely have a round number for your inside diameter. And so, but yeah, thanks a lot for that. Inside diameter. And that's so crucial. And so clients will tell me they've got a 24-inch pipe. I got to find out, 24-inch, I believe that's always when you're over like 14 inches, I believe the 24 is going to be outside diameter. So then based on your dimension ratio or your schedule, you've got to get the ID. And so, yeah, I'm always like, what's your dimension ratio or what schedule pipe you're using? So yeah, I got to get the ID for sure. Yeah, good point. Yeah, so a lot of times people will be asking us for the pump head. We just had a client the other day who wanted to know like the pressure coming out of his system. It was an air system, and it's just like a fan. It's a very low pressure system, and they were modeling, like from the outlet of the fan to the outlet of their pipe, which discharged to the atmosphere. Just think of it as like an 8-inch duct, maybe 200 feet long, and they wanted to know the pressure in the system. When I hear that, I'm like, where do you want to know the pressure in the system? So, he sort of was just thinking, by default, outlet of the pump. And that's fine if you want to know the outlet of the pump. If you actually want to size the pump, depends on your pressure at your inlet of your system and also any piping that gets you to your pump. So you'll have some pressure losses getting to your pump inlet. And so, don't just ignore those. Don't say that your inlet is 0 PSI, atmospheric. And so then if it was, then okay, true, then your outlet of the pump is going to be your pump head in PSI. But if you've got some losses entering your pump, you're going to have a negative gate pressure entering your pump. So you're going to need a little more pump head to account for that negative pressure entering your pump due to your piping and so on prior to the pump. So yeah, just kind of moving along here. So I'm going to click back on the home page. And so we also do so this is kind of a fun one. If you want to include a pump curve. So a lot of folks, I'll be told by a client, we need so many, I'm talking in gallons per minute because that's English units, because that's what I'm kind of familiar with what they mean as far as the bigness of them. But yeah, I apologize if you're in the international community where you're not just doing the English units, obviously. So somebody will tell me like the gallons per minute of their system and say, here's the system, what size pump do I need? Well, this is kind of this program is an intersection of the system curve, which is what you get by using the previous program, and actually using a pump curve. And so we simulate pump curves just with a simple equation like this. Now, it's not, if you go to a pump curve, supplier or manufacturer, they're going to give you a curve. And so, it's not going to quite look like this. This is just like a second order approximation of sort of a generic pump curve. And, but you can put into our program like the max point for the head and the max point for the flow. And our program will fit a nice sort of parabolic curve through those points. And then it'll intersect it with the, what we call the system curve, which is analyzing the system at different flow rates. So you get a curve. Do I have a system curve on here? I guess I don't. System curve goes in the opposite direction. So a system curve would start at, say, 0 head and 0 flow. When you have 0 flow, there's no head required. There's no flow. But then your system curve kind of goes, I'm just going to sort of move my cursor, would kind of go in this direction. And so the intersection of the system curve and the pump curve gives you your operating point. So that's the actual flow rate and head that will go through that system with this pump. See anything else on that? All right, so yeah, let's just keep moving along. So we also have calcs for Hayes and Williams. This Hayes and Williams is a friction loss method used by mainly civil engineers going back 100 years. And the C coefficient for Hayes and Williams is completely empirical. People did experiments on pipes where they wood stave pipes, plastic pipes, steel pipes, pick your pipe, and there's a C coefficient for it. Come down here, for instance, copper pipe, your C coefficient's like 130 to 140. Galvanized iron's a little lower. Lower number means rougher. So glass is smoother than galvanized, so it's like 140. Lead, whatever. Plastic, 140 to 150, pretty smooth. You know, these are kind of for materials that are newly put in a system over time. You know, especially in the water industry, you're going to get calcium and magnesium and other multivalent ions plated out on the inside of the pipe. So your pipe will actually get smaller diameter over time, and also will have a little different roughness on it because you no longer have the water contacting the actual pipe material. You have it contacting those precipitated ions that are sitting on the inside of the pipe wall. And concrete, a little rougher, so on. So this, you know, basically the fundamental equation is the same as using Darcy-Weisbach, which I showed you on the previous screen, but your friction loss equation is different. So here's the friction loss equation for Hayes and Williams. This may or may not look familiar. You can see it in different forms. Sometimes it's shown in terms of diameter. Sometimes it's shown in terms of length on the left side. And so they'll combine some of these coefficients and maybe different units. So I believe this diameter is in feet and the head loss is feet, velocity feet per second. But if somebody's got diameter, there's plenty of equations out there with diameter in inches and with different coefficients. So it's one of these equations, you know, you just hope like the book's got the coefficients right. And so, you know, if it's not an equation it's not a form of an equation that I'm super familiar with, I'll actually, you know, do a calc with the units I know work and the equation I know work, and then use the equation in the book, say, that uses different units and make sure the head loss comes out the same. And so it's an empirical equation. That's why you have these goofy looking coefficients like 0.63 power and 1 over the 0.54 power. You could just punch that out on your calculator and get a roughly 2 or something like that. But this equation had 1 over 0.54, so that's what I used. And so yeah, empirical, you know, these coefficients were determined 100 years ago or more from, you know, Hazen or Williams. But it's the most widely used equation for municipal water distribution, even now, at least in the U.S. There is a program called EPA Net that I mentioned on my other web page that we've done where we've done our consulting. EPA Net is freely available from the U.S. Environmental Protection Agency, and it you know, you can have like 1,000 or more pipes in it, and so it's a pipe network system that basically solves this equation. Or you can select Darcy-Weisbach for your friction losses. It just solves this equation from node to node along pipes with valves, with pump curves, all kinds of stuff. And so we use EPA Net a lot. The software we sell on our site is way simpler than like EPA Net. So this is just a single pipe solver right here. We do have a pipe network program that I'll show you in a little bit that has, say, maybe 12 pipes. So, you know, we're not trying to compete with like EPA Net or other commercial software that does, you know, thousands of pipes. And there's a lot of commercial software out there that'll solve water distribution problems. EPA Net, you know, it's free. You know, we're not using it all the time, so it's not really worth us, you know, paying for a commercial license for some commercial software. And EPA Net, you know, does pretty much what we need for companies. The U.S. EPA has done, you know, the U.S. has done, I got to say, a pretty decent job on getting some software out there that's freely available to the engineering community. So EPA Net, anybody in the world, you can just key into Google EPA Net free download or something like that, and you'll come up to the EPA page and download version 2.2. That's the latest, you know, free. You just got to learn how to use it. And then also for the open channel, the U.S. Corps of Engineers, you know, hired some companies 20 years ago, more than that, to write Corps of Engineers. They call it Hydrologic Engineering Center, HEC, RAS, River Analysis System, which, you know, has been used by the Corps to model the Mississippi River, the Missouri River, and we use it for clients for, you know, smaller situations, but it's free. And same with HEC HMS, which is Hydrologic Modeling System. HMS is for rainfall runoff. So you model your watershed, you put in your rainfall, your topography, and all that. It predicts hydrographs, which is flow rate versus time. at various points along the river. And then you can use those numbers to size culverts and so on. So a lot of free stuff out there, which I find very nice, very encouraging that we've got that stuff. So then if you want to get into compressible flow, so one of our more popular programs is this choked flow program from a tank. So you've got a tank here, you know the gas specific gravity, maybe it's natural gas, who knows? You've got its pressure in the tank, that's what the subscript T's are, or tank, temperature, density, and then so you put those properties in, or those values in as inputs, and pipe diameter, pipe length, minor losses.
Can can you hear me, or are you frozen?
Yeah, nope, I can hear you. Am I frozen? Are we good, Paul?
I can hear you fine. I can hear you fine.
All right, I think we're good. I don't know if anybody had a question.
Oh, there's a problem on my end. Sorry.
Okay. All right. So yeah, you put in those your knowns say at the tank, and then this program, you hit the calculate button, super fun, numbers fill in, and then it tells you your mass flow rate, like in pounds per second, or you can convert that over to say kilogram per second, easy peasy. Convert to kilogram per second. Flow rate, standard conditions, that's another one, versus actual flow. People want it's more useful to have the standard. If you do, I always run into people who are like, what's a CFM versus an SCFM? An SCFM, standard cubic foot per minute, that is at a given temperature and pressure. So hence, it is actually like a mass flow rate. It really is think of it as a mass flow rate with some weird volumetric units. In the international community, I believe it's like normal. Means the same as here as standard, maybe actually at slightly different temperature and pressure, but normal meter cube per second. So you know that that's actually a mass flow rate because it's converted to a standard temperature and pressure. And so this will give you the flow rates. It'll also give you the velocities and the Mach numbers at various points in the pipe system, and temperatures. You can have quite large temperature swings as you go through contractions and expansions and so on. And so, this is in Fahrenheit, if you can relate to that. So we go from like 56 degrees down to minus 18. So it is important to, this does show the importance of using a compressible gas calculator, because it'll account for different densities with those temperature and pressure differences. Yeah, so choked flow, this is another popular one, gas leak rate through a hole, one that you can just code up on your own pretty much. Sometimes we do simple calculations and they sell pretty well, frankly, but then we also have the really complicated ones that take us years and they sell, maybe worse. So it's weird. We spend a lot of time on a calc that we think like nobody has, but there's just not that much of an audience for it. So the ones that are like this, that, it's pretty much a one-liner down here, that it's a little complicated, but you can code that up in a spreadsheet. Just be careful with your units and your powers and all that. But you can code it up fairly easily in a spreadsheet. But we're a time saver, so you pay $40 and you get access to our software, and maybe it saved you 10 hours of time of coding up those equations on your own. So what we're selling is time, basically, for folks. So so for this one, you've got a leak in it. So you got basically a tank or a big or a pipe that's fairly large compared to the outlet hole or the pinhole or whatever you might have. Pretty popular program, for gas leaks. You do need to know the area of your hole or the diameter if it's circular, and you need to know the pressure and the temperature. K is the isentropic ratio. You look that up in a book for your specific gravity liquid or gas for the gas that you have, and S is specific gravity. And so, if you know those parameters, you can hit, your numbers here, hit calculate, and it'll tell you, here's your mass flow rate coming out. And then you can figure out, how long you've been having this leak and if the pressure's been fairly constant in that tank over the period of time. And so you can know how many pounds or kilograms of gas has leaked out that hole over a given period of time. We've been working on for several years an unsteady calculator where you have like where gas pressure is decreasing over time in the tank. And so you start with the known pressure, and then as gas goes out of the tank, since the volume is fixed, you're losing pressure in the tank over time. In actuality, if it's a huge tank, then you can maybe have fairly constant pressure in there. But in most cases, you are decreasing pressure in the tank over time as gas goes out. And so for like 2 years now, we've been working on a gas depressurization tank calc to tell you how long it takes for the pressure for all that gas to get out of the tank and the rate that is going out. So a nice graph of, say, pressure versus time. But like I said, we're getting a little burned out of writing software, and so I don't know if we'll ever get to that one, ever get it finished. But Debbie's got her part so much done, and my part is like to check it and to pretty it up a little bit. And it's like, oh man, are you kidding me? Software. So well, there you go. So if somebody wants to write a pipe depressurization calc, I think there's a fairly decent audience out there to buy it. I don't know. But I mean, other oil industries all over this stuff, they got their own software for it. But, we're a different just another source of software for people to, consider buying. Bernoulli equation, very applicable program, fairly popular. Does a lot of cases. So you can model like a pitot tube. If you're measuring velocity in a pipe using a pitot tube, it'll tell you the velocity based on the pressure on that pitot tube. Flow over a dam, flow under a sluice gate, a hole in a tank. So these are constant densities, so they're not as complicated as the compressible that I just showed you. Simulate a Venturi nozzle or orifice meter with a fixed orifice discharge calculation. We've got other calcs that do that a little more technically as far as narrowing down that coefficient. But just a very general, you've probably heard of Bernoulli equation. It boils down to a very simple equation. It has no losses in it. So if you're going to use it for real world, you kind of want to include a discharge coefficient or something, but just the simple equation there. So then just a few images of what the program can do: flow over a dam, under a sluice gate, hole in a pipe, going out of a tank, Venturi meter, so on. So just kind of a simple program if you want to get a ballpark idea of what your flow or pressure might be for a given situation, or diameter of a hole in a pipe, say. Let's see what might be fire hydrants. If you all ever get into fire hydrants, a fairly simple program, and really doesn't get much use. People can just keep all fire stations have this equation. So you measure, if you're doing a fire hydrant test, you typically use 2 hydrants, turn one on to measure the flow out of it using sort of a standard pitot tube, and then measure the pressure at an adjacent hydrant. And then you can use this equation to come up with what the fire departments or cities always want, is like this Q sub D, which is what's your flow rate going to be at the residual pressure, whatever, 20 PSI. It's very empirical. It really doesn't do that well as far as predicting real world conditions, but it's been around forever, long before 2006. But I did get the equation out of the 2006 American Water Works Association publication, and it's based on Hayes and Williams. You can see that same 0.54 power. So it's empirical equation, and then how it's applied is all over the map as far as where people have their residual hydrant versus the flowing hydrant. Are they 10 feet apart? Are they 1,000 feet apart? Are you on a cul-de-sac? It's the industry likes it. It's standard stuff. How meaningful it is, I question it. When customers want to expand their water distribution system, they'll run some hydrant tests, so they'll have an idea of the pressure at a hydrant when there's a given flow coming out of another hydrant. And so I'm supposed to design their expansion of their system based on, one data point. It's not that helpful. Other, like static pressure, where you don't have any flow in the system, is kind of really useful, but you do kind of need to know what's going on when there is flow, because, you have pressure losses and things like that. So just using a number when there's no flow is not that helpful. I got about 5 minutes left. Pipe network. So this one kind of competes. I mean, we don't compete at all. We've got 12 pipes, but kind of, if somebody doesn't want to learn the program EPA net, Then, you maybe come here and you could put in like a known pressure at one of the nodes and flow rates that you have coming out of each of the other nodes, and it'll tell you the flow in each pipe, and you can vary the diameter in each pipe so that you can adjust to the sort of head losses that you kind of want in the system or want to minimize, but also want to save on pipe material, so you don't want to go on too big of a pipe. So yeah, so this one's kind of handy. Water hammer. So I was mentioning earlier about water hammer. I find this program really helpful. So we have a program that, let me just go to the other one. So this water hammer program, you're entering like, so you've got a reservoir, maybe 3 different diameter pipes, for instance, and a valve at the end, and you know the time that you're opening or closing the valve. And so this program will tell you the maximum and minimum pressures in your piping system and where they occur. And so, if you kind of have a situation that simulates our image here, then it's good. But what I often use is the instantaneous valve closure equation, because I just want a worst case. So say you've got a pipe that's maybe you've got water and you're closing a valve instantaneously. Your steady state velocity is maybe 4 feet per second. You got an inside diameter of like 7.9 inches, wall thickness of 0.3. It's steel, which sets the pipe modulus, water, which sets the density, and the fluid modulus. Hit calculate. And so you get a pressure different, you get a surge pressure of 233 PSI. So, if you've got a steady state pressure of like 40 PSI in your pipe and you have an instantaneous valve closure, be careful with your design because you may get an additional 233 surge pressure. There may be other places in the situation that can absorb this through surge tanks, whatever, but worst case, 233 plus your steady state pressure, maybe it's 40, so you're up to like 273 PSI that you might want to design for. So that's a lot thicker pipe wall or more serious material than you might think of if you're just designing for a steady state pressure of say 40. As your delta V increases, that number goes up even more. So if you're like at 8 feet per second, then you've got 466 PSI surge pressure. And so this is your worst case. You are instantly dropping that velocity from 8 feet per second to 0 feet per second. So worst case. So, if you don't want to design for this high pressure in your pipe, then you use a more program that's more complicated, like the one where you enter the valve close time and enter more details about the situation. And so maybe you can design your pipe based on a lower pressure. But if you just want like a worst case, then this one's super handy. All right. Well, I think it's probably time to start wrapping it up. Paul, is there anything else you'd like me to share or
well, we had a
comments or
question.
anything?
We had a question in the chat from a member who had to leave, and he was wondering what's the $40 fee? Was that for a month?
Oh, yeah. I appreciate that. Yeah, I've not been following the chat. It's on my separate screen. Yeah, so what the $40 does, and I'm clicking on our purchase pin page. So the $40 gets you 7 days of access for all the calculations for 5 computers. And so so you would click on that here. Then if so our next option up, maybe you want to buy for 90 days. So then that's $90 to access all the software, all 80 programs for 90 days. And then we've got our more expensive option of a year for $200. So you get all the programs. Yeah. Yeah, we do get the question, what if I only want to use like one calculator and you've got 80 of them and I still got to pay your $40? Yeah, I mean, we thought about, having pricing where we get down to like $1 for one calculation for 2 hours or something. But, tracking all that, it just kind of seemed a bit unwieldy. And so we're just kind of going with these pretty broad options. Yes. Retention ponds, I'm seeing a question about that. Yeah, for sure. We got some calcs on there for that. Let's see, let me just scroll up.
Bill asked a future topic: 10 most common mistakes made computing pressure loss in pipes.
I would say not writing your equations out. You gotta know how to write your equations, and you've got to write them correctly. And then you've got to write a solver, a program, Excel, or do it by hand that follows those equations properly. So everything's, you got to know the, the engineering of it, and you've got to do it, and you've got to solve it according to the equation you wrote. Usually people don't even think about writing an energy equation from like location 1 and 2. I'll get these schematics, CAD drawings. There are all these little lines all over the place. Like, come on, man, just draw me like pencil on paper and draw me like where you want your pressure where you want me to start my calculation for your pressure loss. Put a 1 on it. Like in the middle of this pipe somewhere. And then somewhere you've got a pipe, maybe it wiggles around. Draw the wiggles for me on pencil and paper, and then draw me a pump if there's a pump in there. If there's any pipe diameter changes, give me lengths, diameters, pipe material, and where it discharges, or where you want me to calculate the end pressure. It may not be at the discharge necessarily at the pipe. So draw it. Give me a beginning and an end, and I can write you energy equation forever and ever. I'm really good at that. And then once you give me the schematic, the drawing that I understand, we are good to go. And but I gotta have that, and I've got to know if it's a gas, I got to know specific gravity, a little bit about your starting pressure, temperature, stuff like that. Yeah, it really does come back. I don't like to say back in my day, but it does. It comes back to really fundamentals, just kind of understanding stuff. I feel like people going to college today, they're getting that for the most part. But I do struggle with the lack of a good report that accompanies the spreadsheet. When I run EPANET, it will give me a pressure at the end at each node, and I for sure will run our little bitty calculation for a single pipe against to verify that EPANET gave me the proper pressure loss between those two nodes for that diameter, length, minor losses, whatever. So I will always make sure, because maybe I selected by accident defaults for EPANET that were SI, and I wanted to use English units, something dumb and fundamental like that. And because maybe I'm just using a previous project, bring it up, and I kind of forget that the new client wants different units or whatever. And so, man, I always check against another calc for a canned program. Yeah.
A little finger slip can be quite expensive to fix if you don't check things.
We are, I'm not going with paranoid, but really careful about sending stuff out of our office. When somebody sends me an email, can you just check this real quick? My mind is like, real quick. I don't really do real quick. I will take my time and maybe ask them to pay, if it's going to be like 15 minutes, whatever, I'm not going to ask them to pay probably, but I'm not going to do it quick. I'm going to do it careful. Another thing with that in mind is, because I don't know if our calculations are, like you said, the end of their calculations for the system. So I will often give them a result in four significant figures, like 2.345 or something like that, instead of rounding that, because if they're going to use that number later on, I don't want them to lose any precision as they go.
I've often been curious about liquid flow and pipe, or even gas flow. Are most designers targeting laminar flow or turbulent flow?
Yeah, generally turbulent flow. Yeah, pretty much, because it's if your pressurized pipe, turbulent flow is anything with a Reynolds number over about 2200, and so pretty much everything in pressurized pipe is turbulent, and open channel is pretty much always turbulent. But if you're dealing with really low velocities and maybe high viscosity, I believe fluids, high viscosity, because Reynolds number is like rho VD over mu, where mu is your viscosity. So very high viscosities, you're going to get laminar flow. But generally, liquids, gases, oil, water, probably going to be turbulent. Calculations, theoretical, or need to add specific coefficient. Yeah, it just depends. So generally there is a specific coefficient that's empirical, that is in almost every equation. You can do them theoretically. So like even the Darcy-Weisbach for friction losses, you're using an E value, which is the surface roughness for the pipe, and that was determined experimentally, and actually based on they actually glued sand into the inside of pipes back in the day, and they knew like the sand grain diameter, and so that is what they would call their surface roughness. And then they ran water through or water whatever at a known flow rate and measured the pressure loss or the elevation change, say, between two tanks. And so that's how they kind of came up with diameters of your surface roughness if your pressure and so on didn't exactly match the grain diameter. And then discharge coefficient through an orifice, nobody goes with 1. You got to go with like 0.6. So that's empirical, but it's a very commonly used number that's been tested over the years generally. When people ask what I do, I have come around to calling myself a fluid dynamics person over the years. And it's because we do oil, we do gas, we do water, groundwater. It's too broad to just say I'm a civil engineer or do water resources or mechanical engineering, stuff like that. So yeah, I've come around to calling myself a fluid dynamics person. Just getting back to cavitation real briefly, we've done some work for some people in the hydropower industry, and that's kind of getting a little bit more popular with climate change or whatever. And so with hydropower, you got to be careful about putting your turbine low enough relative to the tailwater in the river so that you don't have cavitation at the outlet of we call it the runner, the outlet of the turbine. And so if you don't consider that maybe you're putting your turbine too high, you're gonna have negative pressure at that downstream side of your runner, and that's gonna cavitate, and your thing's just gonna be loud and deteriorate. So for hydropower, make sure that your turbine is low enough to avoid cavitation. Yeah. So you worry about cavitation at the inlet to a pump and the outlet of a turbine.
Yeah, thank you very much, Ken.
All right, thanks, Paul. Really enjoyed it. If you ever want me back, let me know. Happy to do it.